So for this module, make sure that you remember that carbon can only make 4 bonds. And by this time, before you start this chapter, you should also know how to have a vague idea of what the structure will look like if you're just given a molecular formula. Okay. Now remember that the electrons can be represented by different manner or how you're writing your structures as. So for example, all of you are able to see my cursor. If you look at the first structure that we have here, this is what we have been looking at so far, the Lewis dot structure. Now, if instead of writing out all of these hydrogens individually, what if I have condensed all of these units as CH3? Okay. The next one, the CH2, then the next CH2, another CH2, and then the last chlorine atom. Now, what did I do in here? I wrote out separate moieties. Now, moieties are just chemical structures which are not anything on their own, but can be looked upon as special parts or different parts. So for example, CH3 is a moiety, CH2 is a moiety, and so on and so forth. Any questions on how I condensed all of these, all the 3 hydrogens as CH3, or how both the hydrogens as CH2, and so on and so forth? So if you look at both of these structures, I still have my 4 carbons. However, I also have condensed all of the 4 carbons and their hydrogens in something like this manner. I'm not counting chlorine as any of my main chain atom. Okay, why? Because one of the hydrogens which were supposed to be on this carbon have been substituted or replaced by this chlorine. Any questions on what I just said? So one of the hydrogens, this carbon, has to make 4 bonds. 1, 2, 3, 4. The 4th bond is usually with a hydrogen, but that univalent hydrogen has been replaced by a univalent halide. So that is the only difference that I see in this structure. Because it is not a hydrogen, I have to write it out. Okay, so any atom which is not hydrogen or a carbon has to be written separately. Now, when I write chlorine here, it always indicates that this atom belongs to the carbon, which was right before it. Not to the carbon coming up, but to the carbon before it. Always, always remember this. So there are 2 things that you have to remember. Carbons and hydrogens can be grouped together. Any non-carbon hydrogen atoms have to be labeled separately. And then the group or atom always belongs to the carbon just before it. Okay, so these are the 3 things that you have to remember according to this. Now there will be questions for you that from the Lewis structure, write a partly condensed structure. And this is what we have done here in this particular question. Now from here, I will go and show you what is a condensed structure. Let's do the condensed structure first. Now, what did I do in the completely condensed structure? Though condensed and partly condensed, what is the difference between these two that you are seeing? The only thing that is missing, somebody wants to answer that?
Oh, I was just going to say the bonds aren't there.
Exactly, that's right, Nelson. Very good. So the only thing that is missing is between the moieties or these smaller parts, the bonds are missing. We are not showing any bonds in between these groups anymore. Okay, very good. So from Lewis structure, you can write your partly condensed. From partly condensed, you can write your condensed. Now this condensed can be super condensed also, or the actual condensed form. How is that? If you look again, this CH2, this CH2, this CH2 are repeating themselves. And so how many times the CH2 unit has repeated itself? It has repeated itself 3 times. And the chlorine is still written at the back. Why? Because chlorine is attached to the carbon right before this chlorine comes. Remember, this chlorine is attached to the carbon right before the chlorine comes. So the condensed structure, this is one of the correct versions of writing the condensed structures. And we will look at more condensed structures. But you need to know and recognize that from a molecular formula, you will do the usual to figure out your Lewis structure. And then you can write a partly condensed structure. And then you write the condensed structure. Or if you don't want to go to condensed structure, you can do the bond line structure also. Now, what is this bond line structure that I'm talking to you about? Now, first of all, this is not the square kind of structure that we have usually seen, especially in our module 1. So far, we were just writing our carbons flat out. However, in reality, and we had seen this last time we had this class, that a sp3 hybridized atom will have a tetrahedral shape. What does that amount? It means that 2 of your bonds will be in this V form and 2 of your bonds will be in this V form. Now, this is the structure that you are expected to see. This bolded, dashed bond. And then a dash bond. What does this center indicate? If this is the carbon that we are talking about is the sp3 carbon or the tetrahedral structure carbon, both these red bonds are in the plane. Now just look at your own hand. If you look at the flat portion of your hand, you elongate it all. And let me show it to you on screen. So let's say that this is the back of my flat of my hand. And these are the 2 bonds within this plane. So within this plane, I have the 2 red bonds. And now one of the brown bonds is coming out. One of the brown bonds is going in one direction, and while the dashed is going in the other direction. How do I know which is which? The bolder wedge bond is coming towards you. If this is my flat hand, my flat portion of the hand, both the red bonds are in this plane, the bold wedge is coming towards you, while the dash bond is going at the back. So it is a V. There is no doubt there is a V here. One of the fingers is coming towards you. One of the fingers is going at the back. Still a V. But the way we are looking at it is a little different. Any questions on this? All right, very good. So going back, both of the red bonds on this carbon are in the plane, whereas the bold wedge bond is coming out while the dashed bond is going at the back. Now, we don't worry about these as much. We are worrying about this valley or this zigzag shape. So looking back at our partly condensed structure, how many carbons do we have? I'm going to count 1, 2, 3, 4. So in my bond line formula also, I need to have 4 carbons. In a bond line structure, each dot is considered as an atom. This dot or this atom is specifically labeled as chlorine. Remember, all non-carbon hydrogen atoms have to be labeled. I'm sorry, somebody had a question? Okay, don't worry. And so each of these dots, except for this chlorine, is a carbon. Okay. So we always write our linear chains. Okay, a linear chain is carbon, 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 and the same route, on the same route. Whereas when you will have branched chains, and you will have seen this example in our module 1 also, when you will have branching, the branching will go sideways. So this is your main chain, and this is also a linear chain, but it is branching out from the main chain. So coming back, how are we going to draw this? The line structure has no hydrogens which are shown. So if you look at this carbon, this carbon, this carbon, this carbon, I don't have to show you, but there are hidden hydrogens on these carbons. How many hydrogens will this carbon have? Anyone?
3.
3, very good. Now, even though they are hidden, I have to remember that all carbons have to make 4 bonds. Similarly, this is a carbon. Where are my hydrogens? 2 hydrogens here, 2 hydrogens here. And even though I don't have to show them, and you don't have to show them either when you're doing the bond line structure. Now, pay attention on how I have labeled my hydrogens. If the dot is pointing downwards, both my other bonds, so this is the carbon, 1 bond, 2 bond. The other 2 bonds that this carbon can make will be shown upwards from this point. If the carbon is pointing upwards, then I will show the rest of the 2 bonds also upwards. Okay, because I have to make 2 V's inserted in each other, pointing in opposite direction and at a intersection to each other. So whenever you're writing a bond line structure, always remember no hydrogens to be shown, but you have to show all non-carbon hydrogen atoms. So for example, if I have this structure, I am writing the hydrogens with my nitrogen, right? How many carbons are in this particular structure? Anyone?
3. Hello.
Yes. Okay. I see some, but I was just reading the chat also. Yes, there are 3. How do I know? Because there are 1 dot, 2 dot, 3 dots. To the third dot, my N is attached. So I have 3 carbons. How many hydrogens do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if I have to write the molecular formula of this compound, this is how I will write it. Or I can also do another thing. Instead of counting all the dots, I can actually write here on the line structure. Because if I am given a bond line structure and I have to figure out the molecular formula, I can do anything to it. I can go to any sequence, which will make my life easier for me to figure this out. And so I do C3, 3 plus 2 plus 2 is 7, 8, 9, and then nitrogen. I can do this also. Okay. Any questions so far?
Would writing it like the condensed structure in the middle be wrong?
It's
Like with
not wrong. I'm sorry, Dahajia, go ahead and repeat your question, please.
I was just asking like with the parentheses and stuff, like you see how you wrote C3H9N? Could I have written like CH3, CH2, 2, NH2?
So you can, but again, you have to remember to read the question. If you're being asked, for example, from bond line structure, I can ask you to draw a Lewis structure. From the bond line structure, I can ask you to write a condensed structure. From the bond line structure, I can ask you to write the molecular formula. You see what I'm saying? Or a partly condensed structure. And you know, from a partly condensed structure, I can ask you to write a molecular formula. Or from a partly condensed structure, I can ask you to write a bond line structure. So, you know, we can give you one type of structure. You should be able to recognize what that kind of structure is. And then you will figure out what the question is asking you. If it is asking you about the bond line structure to be made, or a Lewis structure to be made, or a condensed structure to be made, so accordingly, you have to answer that. Does that answer your question?
Yes, ma'am. Thank you.
Okay, very good. So the other thing that you have to remember about this is, oh, I deleted it again. When you have your bond line structures, every dot is a point. Let's write that also. Okay. So bond line structures are very easy to look at. But all you have to do among all of these structures is that you have to maintain the connectivity information. Make sure that you label your structures. Okay. So this is just the repetition of what I told you about the parentheses. Whenever a group is repeated, we can write and we should write all the repeating units if they are together only. That's one of the things. If it is like CH2 and then something else, you cannot combine these two CH2 units. Okay, there is a difference between here, unless there is symmetry. But just remember that all the repeating units have to be together. So when a group is repeated consecutively, you can use parentheses for that moiety or a group, and then you write in subscripts how many times it was repeated. The next thing is when there are two groups of the same type, they both are attached to the atom before them. So how would you write this out? There is R, and if I have to write the partly condensed structure, when I have a partly condensed structure, I will have bonds between each unit. So between RCH, remember this H will stick with the carbon. It will not exist on its own. And then I have how many CH3 units? I have two CH3 units. Both of these CH3 units will belong to the carbon before them. Right? So both of these, to this, two CH3 units are attached. Both of these are attached to the carbon before them. Okay. Any questions so far? Now, when a complicated group is attached, you have to be a little bit more careful. You can use parentheses at that point also. Now, before we go here, let me show you something else. Let's say that I have 1, 2, 3, 4, OH. How will I write this bond line structure as a condensed formula or a condensed structure? Now, before I build or give my answer, I will have to build up. I cannot just straight away think about, oh, this is what it is going to be. What I will do is I will write CH3, C, CH2, CH2, CH3. Now, do you all understand these CH2s, these CH3s? Because carbon needs to complete all of its 4 bonds. Let's pay attention to this carbon. How many bonds this carbon is making? 1, 2, 3. So how many other bonds are left to be made? Only one more, which will be for the H. Now I can see better before I write my condensed structure. I will again rewrite it without bonds. Let's do that. CH, OH, CH2, CH2, CH3. Now this is something that I have to show in my work. If you show me this and you have not shown me the answer, I will still give you partial points just for the fact that you were trying to complete your work. Okay, this is not the answer. Definitely not the answer. This is not the condensed version at all. However, I will give you points because you were trying to solve for it. And this is what I want you to understand also. If you're given a line formula, you cannot right away jump to the answer. Some of you might be able to do that, but most of us have to go through these steps. Anyone willing to give me the answer for my condensed structure? No, not yet. Okay, let me show you. So I'm going to write my CH3 first, and then I will write my CH. So remember, the OH is attached to this carbon. So I will write in parentheses OH. After I've written OH, I will keep continuing my chain. I have two CH2 units, and then I have one CH3 group. So all of this will be written at the same line. It should be written in the same line. So my answer for the condensed version would be something like this. Any questions? Now, whenever you're doing this, time permitting, you should always check back. If I have to redraw this structure, how will I redraw it? I will have my CH3s. Oops. I will then have my CH. And then I have this OH. Where does this OH go? To the front carbon or the back carbon? To the back carbon. So I've taken care of these also. Now I have to repeat the CH2 twice.
I have a question.
Please go ahead.
Is the connecting group OH always going to be in parentheses? Like if the problem asks us to draw out the structure, is the connecting group always going to be in parentheses, or are we going to have
Usually it will be. Usually it should be. Even if it is a Cl, I would write this Cl in parentheses. But if it is not, let's say for by chance that there is a group CH3, CH, Cl, CH3. Even if you have a system like this, can you draw like this? Can you have your chlorine inserted between two carbons? Sydney?
Oh, no.
No, right? And so you know that this is not going to happen. So even if it is not in parentheses, you need to remember that this Cl belongs to the carbon before it.
Okay, thank you.
Right? So having this parentheses will help you and me look at the structure better. But there might be times that the Cl or OH may not be in parentheses. At that point, you have to remember that, okay, even if your oxygen can be inserted between two carbons, what about the hydrogen then? Can you have a pattern like this? No, we can't. So in our main chain or the main flow of the chain or the main linear chain, you cannot have O and H next to each other. It is wrong. Hydrogen cannot make two bonds. Chlorine cannot make two bonds. So the only reasonable thinking would be that this OH is together and connected to the carbon before it. Okay, very good, Cindy. Any other questions? Okay. Oops. So let's try to do the condensed structure. So this is a partly condensed structure, and this is the bond line structure. How did I make my bond line first of all? So I have these 1, 2, 3, 4, 5, 6. 6 in the main chain or my linear chain. So 1, 2, 3, 4, 5, 6. Now we have not done the nomenclature yet, but so you are free to label or number your main chain atoms as you like or from wherever you like. Now there are 3 other atoms branching away from the main chain. So I will label them as A, B, C. And you can label them anything you want. I just want to make them look different. So on the fourth atom, I will draw out a bond. Now this is one carbon right here. And this is one carbon right here. So this is going to be my B, both of these, A and B. Oops, sorry, C. So I have just labeled my atoms. So I will compare. On the first, I just have a CH3. So I can just put my dot here. On the second, I have my oxygen. So I'm going to place my oxygen here. On the third, I have just a CH2, so I can place my dot. On the fourth, again, I have a dot, dot, dot. Then I will connect these bonds. Remember to use the zigzag notion for your bond line. All the non-carbon and hydrogens have to be labeled. All the carbons are dots. Another rule that I want to introduce right now for your bond line structure is you have to show your formal charges and lone pairs. Always make sure that you show that. So with oxygen, you must show both the lone pairs. Okay, as we will progress this course, I will keep reminding you, carbon has 4 bonds, nitrogen has 3, oxygen can make 2 bonds. Lone pairs, lone pairs. Always remember this. This is the basis of organic chemistry. Now, since we have figured out our bond line structure, how about from this if we have to make a condensed structure? Okay, I'm going to give all of you a few minutes, like a minute. Why don't you all try to write a condensed structure on your own? And there are many ways by which we can write a condensed structure. Okay, go ahead and try to do that. Did anyone try it?
Could you share screen?
Oh, okay, sure. Actually, Sydney, that's a very good. That's a very good way of depicting it, and that is, as I said, there are multiple ways. That is the correct way. That is one of the correct versions. I would give it a correct version. Yes, very good. Anyone else wants to share their answer? Okay, Armani Pace, are you here?
Yes.
All right, Armani, can you help me with this one?
Okay, is it CH3 in parentheses and then 4?
Hold on. Sorry, CH3 and then?
In parentheses with the 4. I mean, that puts CH3 in parentheses and then 4. Because there are 4 of them, right?
Could you repeat that? Do you want to annotate it and show it to me? Do you know how to do annotations?
No.
Are you on your laptop?
Yeah.
Okay, so go on the top. There is or in the 3 dots, there will be a annotate kind of a thing. So Nelson, parentheses inside of parentheses, that may work, but don't overuse it.
Oh, there we go.
Okay.
Okay.
Very good, Armani. Yes, you're doing it. Go ahead. Yep.
Mine's kind of big. I didn't mean it for it to be this big, but. I'm gonna just write under it because I can't fit it next to it.
That's fine. You can go ahead and write under to it. Don't worry. I'm just looking at chat for someone else and reading if their answer is correct.
Is it like that?
Okay. Now, don't worry about the structure that I made. I want you to rewrite or answer back what you have written here. Okay. So this indicates that there are 4 CH3 groups attached to the same something. Okay. So when you write 4 CH3 groups, you have to remember that these CH3 units or moieties are farther away. They are not consecutive. They are not next to each other. So when we write CH2, CH2, when we write something like this, we indicate that both the CH2 are next to each other, not like this. Oops.
Oh, okay.
Not like this. So make sure that both the units are next to each other, not anywhere in the group. Because if you're indicating that, then we can have so many CH3 units and so many other CH2 units, right? So you have to make sure that it goes in a flow. And if I rewrite it, I should be able to rewrite what I initially wanted or where I started out with. Okay. So let's try to do this as a class. I'll do CH3 and then I'll write O. No hydrogen to write with it. I then have a CH2 and then I have this CH. Okay. And now to this CH. Yes, go ahead. Somebody had a question. Somebody had a question. Okay. Now, some of you showed this to me and it's completely fine. And let's try to Okay, I'm gonna shift gears and I'm going to show you this on my paper. Okay, so CH3, oxygen, CH2, CH, and then to this CH, some of you did the parentheses and you wrote this CH, and to this CH, two further CH3 units are attached. So to this CH, some of you did a double parentheses. Who does not understand what I just wrote here? Armani?
I got it.
Why did you do the double parentheses there?
So some of you have shown it to me, and I just wanted to show it to the rest of you, that it is also a correct way of writing a condensed structure. So this CH and then this CH right here, and then these two CH3s are attached to this CH, and that's why I wrote 2, because both of them are to the same carbon. And now this CH2 and this CH3. So this is one way of writing it out. If I will expand it again, I have CH3, my oxygen, my CH2, my CH, and then I have a big chunk on this CH. Let me deal with it later. I have this CH2, I have this CH3. So now I want to deal with this big chunk, which was on this. This big chunk is on this carbon.
So basically anything in parentheses is attached to the thing that's before it.
Yes,
Right.
except if you have something like this. If the parentheses is the first thing, then this chunk will belong to this carbon. Otherwise, for the rest of the time, everything else will belong to the carbon before it, or the atom before it, the multivalent atom before it. If I have to write it out in my expanded version, I will write this CH first, not this CH3, but this CH first. And to this, I will attach both my CH3s. You see that? Who had asked this question? Are you?
I did. Yeah, I got it. Thank you.
Okay, very good. And so if I'm writing this back, I will write this CH first, because this and this are going to attach to each other. And then this CH3s, these two CH3s belong to this carbon. So this and this structure match. Another thing that I could have done was, instead of going or using this as my main frame, I could have used this as my main frame, right? Using this as my branched substituent and one of these CH3s as my branched substituent. I'll use this. So 1, 2, 3, 4, 5, 6. So let's do this. CH3, oxygen, CH2, CH. To this CH, this group is attached. And isn't it easy to see? This chunk belongs to this CH. This chunk belongs to this CH. Furthermore, CH, and then I have to write this CH3 for this CH. This CH3 for this CH, followed by a CH3. Now these two CH3s, I can also write them as CH, and both of these combined together. Why? Because both of these CH3s belong to the same carbon. Both of these CH3s belong to the same carbon. So to this structure, you can write condensed structures in any of these manner, as long as they will, when you expand it out, it goes back here. So, you know, one of the questions that you might see on your exam is that you will be given a couple of condensed structures. You will be given a structure and you will be asked, which among these is not the condensed structure form? For example, the oxygen might be at a different location that for that answer, right? I could have just moved the oxygen somewhere in the wrong place, maybe.
I have a
Or some.
question.
Go ahead, Sydney.
Like, you know how you numbered it 1, 2, 3, like CH3 is 1, O is 2, and CH2 is 3. So do you always start from left to right?
Not always, not always. Just because English is written from left to right, that doesn't mean that we always look from left to right. And that is something that we will cover exclusively in nomenclature. For this module, I'm writing these numbers for you to be able to see the labeling. That's all. This is not proper labeling, of course, but you know, if you label it, you will be able to count it. This is 1, this is 2, this is 3, this is 4, right? The same carbon. This is my 5. This is my 6, and probably the 7th. Both of them in the same group. This is my 8, this is my 9. 8, 9. So I'm just labeling it so that you also keep a count. If I have 9 carbons or 9 or 8 carbons in this structure with 1 oxygen, in your condensed structure, you should have same number of carbons and same number of hydrogen and same number of oxygens also. Right? Having hydrogens is easy, but having a count of these carbons and oxygens is a little bit. Any questions? Okay. So remember your condensed, partly condensed line structures. Now, when you will have double bonds, you will still be using the zigzag notions. How will I write this in my condensed version? I don't have to go about and directly write my answer. I can work on it. So each dot will be my carbon. Each carbon has 4 bonds. This carbon, which has the double bond, has already 1, 2, 3 bonds. And so my 4th bond will be the hydrogen. This carbon also has 1, 2, 3 bonds. So 4th will be my hydrogen. This needs both hydrogens. This needs 3 hydrogens. And so I can write CH3, CH, double bond, CH, CH2, CH3. And if I have to write my condensed version now, I see my CH units are being repeated. CH3, parentheses, CH, twice, CH2, and CH3. I don't have to write my C double bonded C.
I have a question.
Go ahead.
When you draw the double bond, does it always have to be in the inside of the bone line structure?
No, no, not always. Now in this, your double bond is an internal double bond. Sometimes we have what is known as a terminal double bonds or triple bonds also. A terminal double bond will be at the end. Now my condensed structure is going to change. This carbon, this carbon, this carbon, this carbon, this is a carbon. And so how many bonds this carbon will have? Go ahead, tell me.
4,
Yes, and how many hydrogens will it have?
3,
3. How many hydrogens will this have?
2,
How many hydrogens will this have?
2,
How many hydrogens will this have?
1,
Very good. How many hydrogens will this have?
1.
Uh-uh.
No, 2.
So it already is making 2 bonds and it will have 2 more bonds. So 2 more hydrogens, right?
Mhm.
Now let's write the partly condensed and the condensed. So this is my answer. I can still write my partly condensed if I want to, but I'm fine. CH2, CH, right? This is my CH, or if let's keep it that way. CH2 double bond, CH, and then I have 2 CH2 units, and then I have a CH3. This is not my answer, but I'm leading up to that. So I'm writing CH2, CH, 2 CH2 repeating units, which are next to each other, and then CH3. So this is my condensed formula or condensed structure answer. But if you look, if I have a triple bond, I'm sorry, an internal double bond, or if I have a terminal double bond, I can always see that also from my condensed structure. Because when you will start to draw this out, you will see this is a carbon which has only 2 hydrogens. And then you may wonder that maybe Dr. Verma did a typo. But then you will look at the next carbon also, and you will say, no, no, this carbon should also have 1 more hydrogen. And that's the time it should strike you that 2 hydrogens are missing. You are having unsaturation. There is a degree of unsaturation or hydrogen deficiency in this molecule. And that's why you should have a pi bond or a ring in the system. But because the hydrogens are missing from both of these carbons, so probably the pi bond is between these 2 carbons. Okay. So writing double bonds internally or terminally, you will still use the zigzag motion, the zigzag format. But when you will write the triple bond, you have to be a little careful. So carbon, carbon, triple bond, carbon, and then carbon. When you have a triple bond, you have to remember the hybridization of a triple bonded carbon. How many electron domains are around this carbon? 2. If you have 2 electron domains, what is the hybridization of that atom? S and a P. 2 domains, right? Any questions on this? I hope not. But if you still have questions, this is a good time. What is the bond angle associated with the sp hybridization?
180.
180, very good. Since it is 180, you have to show it in the linear manner. Similarly, this carbon will have a 180-degree angle. So this is the correct form of showing a triple bond, whereas this super strained form is the incorrect way of writing a triple bond. Okay, because there's indicating me that you don't know that this is a sp hybridized structure. For your double bonds, you can still have 120 degrees in this way. Because with your double bonds, there will be no wedges or dashes. When do you have wedges and dashes? When you have a sp3 carbon. When do you have no wedges or dashes? This is a planar structure. This is a sp2 atom. Planar structure. All of these are in the same plane, same flat plane. But when you have a triple bond, you will always show it in a linear manner. Any questions so far? Okay, I'm assuming that all of you are understanding everything. Okay. All of you see this structure. I want all of you to draw this structure. This is a bond line structure, right? So I have two questions for all of you. What is the HDI of this molecule? And what is the molecular formula for this compound? Go ahead, I'll give you a minute. The HDI. If you want, you can go ahead and write your answers in the chat, or you can send it privately to me. HDI equals, and molecular formula equals. You know what is a molecular formula, right? You all will have to tell me if or how many carbons there are, how many hydrogens there are. HDI. So you can just copy in your note. Very good, Sydney. Meisha Ren, are you here? Or am I saying your name wrong? Oh, please go ahead and unmute yourself. That's fine, I'll help you, don't worry.
Okay.
Yes, so Meisha, do you remember what is the HDI? The deficiency index, right? How do we recognize HDI from a structure?
By looking at the bonds and rings.
Pi bonds or our ring. Very good. And so if you count the number of pi bonds here, how many pi bonds do you see here? Mm-hmm.
3.
Very good. And everybody, this is pi 1, pi 2, pi 3. Remember the first bond between these two will be a sigma bond. Very good, Maisha. Let's look at the molecular formula. The only elements present in this structure are a carbon and a hydrogen. So let's look at the number of carbons first. So do you want to go ahead and tell me where are the carbons or how many carbons are there?
Is it 4?
So this is 1. How many? So each dot is a carbon. Now tell me, Misha.
5.
1, 2, 3, 4, 5, 6. You see that? Oh. So each dot is a carbon. Always remember that. Do you understand this part, Mesha?
Yeah.
Okay, very good. Thank you, Mesha. And sorry to put you on spot. I don't mean to interrupt. Look, this is the way we are learning, and this is something that we just did. So I don't expect all of you to memorize it instantaneously. But you know, just for a little bit more practice, I want all of us to look at it. Okay. Hyatt, are you here? Okay. I forgot what was the complete name that she was using. Black woman in charge. Are you not Hyatt? Okay. Michaela, are you here? Michaela Thomas.
Yeah.
Okay. Michaela, can you help me count how many hydrogens do I have?
Sure.
So if I look at this carbon right here, how many hydrogens will be on this carbon?
2.
Very good. And how many hydrogens will be on this carbon?
3. Oh, sorry, 1. I was looking at the wrong one.
That's
1.
fine. This one?
None.
None. Yes, none. Because this carbon is already making the 4 bonds. Very good. What about this one?
3.
Very good. What about this one?
2.
And all of you should be writing it out while I'm discussing and Michaela is helping us. You should also be writing the way these hydrogens are drawn. Okay. How many carbons are here?
There isn't a, well, there's 1 carbon.
Wait, no, sorry. How many hydrogens are here?
There's none.
There's none. And do we have any other hydrogens left on the structure?
No.
What about this carbon?
Does that count?
Of
Oh, there
course
is a
it
carbon
does.
there. But there would be 1 hydrogen.
Hydrogen here also, exactly. Now this is a special case that I want all of you to remember. When you have a terminal triple bond, do not forget about the terminal triple bonds carbon-hydrogen bond. Okay, if you remember your module 1, this carbon-hydrogen bond is the shortest among all the carbon-hydrogen bonds that you have on a structure. Okay, so do not forget this CH. So let's count again. How many hydrogens do we have? 3, 4, 5, 6, 7, and Any questions? Any confusions?
How would the condensed version of this look?
Well, let's try this. Put on a different piece of paper. So I have this double bond here with CH2, C triple bonded CH, and I have a CH2 here and a CH3 here. Okay, so what I'm going to do is I will follow this lane. I have this C here, CH2, C, CH3, CH2, C, CH. How's that?
Thank you.
Okay, you're welcome. All right, so make sure that you practice more of these bond lengths. And let me very quickly tell you about a structure like this also. What is this structure? If I rewrite it, I will have a CH3 here. I will have, this is a dot, so a carbon here. I will have a carbon here, a carbon here. This carbon will have 3 hydrogens. This carbon will have 2 hydrogens, but this carbon has all the 4 bonds satisfied, right? So how will I write the condensed structure for this particular molecule? Anyone? Kiara Weston, do you want to help me?
Can you repeat what you said? I'm sorry.
That's fine. I want to write the condensed structure for this molecule. And I have, used, this is my sequence that is helping me see the structure better. Is it helping you also see the structure better?
Yeah.
Okay, so let's write this is partly condensed structure. This is not completely condensed, right? So how will I write my condensed structure, completely condensed structure?
CH3.
Very good.
C.
C.
Would you put the O next?
Now, there are 2 things that I can do. I can just write O like this, or I can write the O in parentheses also.
And then CH2, CH3.
Exactly. Very good. So if you look at this, CH3CO, CH2, CH3, the CO belonged to this double bonded oxygen. There are no hydrogens here, no hydrogens here. So that should give you a clue that you have a pi bond in your structure. Does that make sense, everyone? Any questions so far? Okay. Because there are no questions, I'm going to move on to our functional groups. Oh, by the way, I did mention to you, when you draw your bond line structures, make sure that you write your formal charges and all the lone pairs also. Now, functional groups is something that I will move through very quickly. If you will pay attention to your pre-lecture assignment, which is due tomorrow, you will see that it emphasizes on you knowing the functional groups and you being able to figure out from general formula what is the functional group. And for completing your PLAs, you can look in your books, in your notes, anywhere. So it's like a take-home assignment kind of a thing. But how fast and how well you learn the functional groups will depend entirely on you, because you have to memorize them. But what is a functional group? A functional group is an atom or group of atoms. What is a group of atoms? Molecules. So an atom or a group of atoms that gives a molecule characteristic physical and chemical properties. Some of the general functional groups that you can think about on top of your head, anyone? Anyone? Go ahead, take a shot. So we use them like for drinking purposes, I guess. Alcohols, right? Alcohols, and then amines. Amines are used extensively in pesticides. And all around us, we are using chemicals exclusively. You know, water, H2O, is one of the most basic form of chemical in its functional group that we are using every day. So functional groups are useful for classifying organic compounds also. And so you will know what is the reactivity. Functional groups will help you know the chemical reactions. And they also form the basis for naming organic compounds. Now we have already started to see the hydrocarbons. Now hydrocarbons, alkanes especially, are not considered as functional groups. Why? To have a functional group, you must have an atom which is different or there is a polarity associated. Have you all paid or have you all looked at polarity at all during our module 1? Remember, whenever you will have electronegative differences, you will have a polar bond. So this is something that we did in our module 1. So whenever there is a polarity associated, you will have a chemical reactive site. So alkanes, which are the saturated versions of all the hydrocarbons, are not considered as functional groups. Alkenes have double bonds, alkynes have triple bonds. What do they help us in? These help us in addition reactions. Saturated, unsaturated. What does that mean, unsaturated? They can be, something can be added in them so that they also become saturated, right? So on this double bond, how many hydrogens can you add in here? If you look at this structure, which I'm pointing out, you can add a hydrogen here, you can add a hydrogen here. So you can add 2 hydrogens on this double bond. On a triple bond, how many hydrogens can you add? On a triple bond, you can add 4 hydrogens. So, you know, some functionality is there in alkenes and alkynes also, but no functionality is present in alkanes. And this is something that we will be struggling out with again when we go to module 8, 9, and 10. So remember this. Another form of hydrocarbons are the aromatic rings. Now, the only kind of aromatic ring that we will be looking at today is a benzene ring. Benzene is a very special aromatic structure, and there are variety of aromatics. We will look at them later on. But benzene is something that you will have to work with this module at least. Both of these are benzene rings. If you look, your carbon bonds between these 2 carbons is now a single bond. Where has this carbon double bond shifted? It has shifted to the other location. And so instead of writing in this manner or this manner, we write benzene with 6 carbons in a ring and a delocalized circle in the middle. So you will see me do this several times. What is this? The CH3 group. What is this? The C double bond O group. What is this? The aromatic benzene ring. Any questions so far? None? Okay. So for your hydrocarbons, these are the 4 groups that you will have to know. You can add easily on alkenes and alkynes. but it is very difficult to add on these double bonds. Okay, and we will look at the aromatic chemical reactions later on, but I want you to remember this. This is a very stable system. Okay, remember functional groups are something that must react. So how are these going to react if they are stable? So we use different reagents. When we use them, we'll go about that.
Can you go back to the previous slide really fast so I could just take a picture
Yes.
of the bottom part?
At the which part?
Yeah, just the alkenes.
Oh, you do know that these lecture slides are on your lecture slides, Sydney?
Okay. Okay.
Okay. Yes, all the lecture slides for all the upcoming modules are on, and this is in your lecture course, Brightspace, okay? All right, so to begin with, we will look at the hydrocarbons. And as I was telling you that all our functional groups are dependent upon how well the reactions occur, or it is because of the uneven distribution of electrons. That is why all the chemical reactions will occur. But if you look back in the benzene ring, there is an even spread of electrons. So every functional group has an uneven distribution of electrons, but stable groups who do not want to react will have a even spread of electrons. So this is something that we will again look at the nomenclature module, but I want you to see how we are labeling our alkanes. So all the hydrocarbons, alkanes, alkenes, and alkynes, as well as the aromatic groups, have names, common names also, that we are going to use. So for example, if you see here, CH4, CH2, CH3, CH3. So this is your alkane and the corresponding alkyl group. CH4 is the alkane carbon, has all the 4 bonds satisfied. However, if one of the hydrogens are missing, just one, this group now becomes the alkyl group. So meth is the root word. The only thing that is changing is the last part or the suffix. Meth indicates 1 carbon. On the other hand, eth indicates 2 carbons. So ane stays, al stays, but what changes is the ethyl. And so on and so forth. Propane or the prop is indicative of 3 carbons. Now, this is the condensed version of this molecule. So the hydrogen is missing from this end. Hydrogen could have been missing from this end also. This is the propyl. This is the isopropyl. So from where the hydrogen is missing gives us the indication. Alkanes in general are labeled as RH, whereas the alkyl groups, they are just labeled as R. And R primes, R double primes. They just are indicative of the fact that they are still alkyls, but all of these three alkyls are different. If I just say R, C double bond O, R, what do I mean? Both these alkyl groups are exactly same. If I have a methyl here, I will have a methyl here. If I have an ethyl here, then I will have an ethyl here also. But if I'm saying that one of them is R, the other is a R prime, I can say that this R is methyl. So this R prime can be anything but methyl. So it could be ethyl, propyl, or anything else. Okay. Any questions on how we define alkanes and alkyl groups? Now, alkyl groups are going to be very, very useful for all of us. We will be using alkyls all the time. Aromatic groups. Aromatic group, and as we were discussing, is the benzene ring. How many carbons do you see here? 6. Each of these carbons, and if you go back and look at this structure that I have in this part, how many hydrogens will this carbon have? 1, 1, 1, 1, 1. What is the molecular formula here? C6H6. And so if one of these hydrogens is missing, so what is the formula of benzene ring? It is C6H5H, R, H. What is the R group going to be then? It is going to be just this part, just this part. And hence, benzene is known as a phenyl. Who does not understand this? Beside your, yes, go ahead, go ahead.
Oh, I was going to ask if you could repeat that one more time.
Yes. So for your alkanes, you need to be able to recognize your alkyl groups. You should be able to recognize their abbreviations also. In this particular set, where we have an aromatic group, where all the hydrogens are present. This is C6H5 and it's 6th hydrogen also. But when you will have your aryl, so these are aryl groups, not alkyls, because aromatics are aryl groups. One of the hydrogens is missing. What is the formula now? It is C6H5 because one of the hydrogens is missing. All the hydrogens were here earlier, but now one of the hydrogens is gone. So the formula is C6H5 and it is abbreviated as a PH, a Phi, or a AR. AR just indicates the aryl group. On the other hand, we also have a group with toluene. You have this ring, all the carbons are sp2 hybridized, but then one carbon is sp3 hybridized. Okay, all carbons are sp2 hybridized here. Do you see the difference? All the sp2, 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 sp2. But this carbon is sp3. So how many hydrogens are on this carbon? At least 2. At least 2. And if there is a third carbon also, this is the hydrogen. If this hydrogen goes missing, it will become C6. H5. Why H5? Because this carbon is losing its hydrogen. And then CH2. CH2. So not from benzene, but from toluene. The substituent is known as a benzyl. It is abbreviated as BN and sometimes as BZ also. Okay, I'm going to stop here, but before we go, there is something, a poll that I want all of you to look at. Are you all able to see my page? So I want you to look at this structure. CH3CO pH. We just did pH, right? And we also did CO right here. So what is the HDI of this molecule? You don't have to write answer to me. I will start the poll in a minute. And that's where you will have to choose your answer. Okay, the poll is in progress. And as soon as you answer the poll, the 3 of you have already answered. All right, I'm still waiting for 6 other students to complete the poll. I'll give you 20 more seconds to answer your question. Okay, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so I'm going to share our results first. If you look, most of you answered 2. The HDI of this compound is 2. Some of you also answered 1 and 4. That was our next popular answer. But I want you to think about it again. Before you actually do this question, did you draw the structure out or did you calculate it? Now, remember what is a pH. If we go back and look, it is C6H5. You can either do the structure, the C with the double bond O, because you know what that was. And then you can draw your phenyl ring and draw your CH3. But is this the complete phenyl ring? Just by looking at the structure, can you figure out what is the HDI here? So you have a pi bond here, pi bond here, pi bond here, and a pi bond here also. So you have 4 pi bonds.
Plus ring.
That enough?
Plus
Very good.
ring.
You need to take into account your ring also. So the HDI of this structure will be 5. On the other hand, if we had counted all our carbons, so let's put it in our formula, which helps us calculate the HDI. 2 times the number of carbons. How many carbons do I have? I have 6, 7, 8 carbons. There are no nitrogens. How many hydrogens do I have? 5, 8. Okay, I don't have to worry about my oxygen, but I do have to worry about adding the number 2. So 16 minus 8 is 8. 8 plus 2 is 10. 10 divided by 2 is 5. So with both our methods, from structure, from formula, I will get the same result. But it is up to you to remember that what pH is. Okay?